with a continuous time. Markov chains. So what I will do is I will construct a process, and I will show that it has some property which I will call the Markov property, and to understand what a continuous time Markov chain will be. So we have a finite set E, and I will construct a process xt from 3 objects. So I will assume that there exists a space, omega fp, and that in this space we have a Markov chain, discrete time Markov chain. So discrete time Markov chain, which I will represent by psi n. And this discrete time Markov chain has a transition matrix which I will represent by P. So I'm assuming the existence of this space, and in this space that we have this discrete time Markov chain. And besides that, we also have a family tau k of IID exponential times of mean 1. And this sequence of random variables is independent from the Markov chain. Right, so I'm assuming that there is this space. So in this space exists in which I have this Markov chain, discrete time, and I have these times. So I have 2 parameters, P, which is the transition matrix, and a function lambda, which takes value which is a function from e to 0 infinity. So it can't take the value 0. Okay? And from these 2 parameters and these 2 objects, I will construct a Markov chain in continuous time. Okay? And the idea is very simple. So what lambda and P will represent? Well, lambda will be the parameter of the exponential time at which you remain in one state. So let's say the idea is that you have your set E. It's composed by a finite number of points. So the process is the following. Once you are in a point x, you remain there for an exponential time of parameter lambda of x, which means that the expectation of this exponential time it's 1 over lambda x. So you remain there for this exponential time. And at the end of this time, then you choose one point y with probability pxy, and you jump to this point. So these are the parameters I mentioned. So once you reach y, you repeat. So you remain in y for an exponential time, now of parameter lambda of y. And after this exponential time, you at y, you choose z with probability pyz, and you jump to pyz. So this is an informal description of this process. Okay, so how do I construct this process? Well, a first observation is that if tau it's an exponential time of mean 1, okay, so these are my exponential times. if I take tau and I divide it by lambda, where lambda it's a real number, strictly positive, then this random variable, it's an exponential variable with parameter lambda. Okay, so okay. So here is your state space E. Here is time. So let's say that you start here at x, and I want to construct this process xt. So by following our rule, so we want to remain at x for an exponential time of parameter lambda x. So what I do, it's I take this first time, tau 0, I divide it by lambda of x, and I get, so here, an interval, which is given by tau 0 divided by lambda of x. And I claim that, well, I say that my process remain on x for this interval of time. I will always take it right continuous. So it starts time 0 at x, and it remains in this interval at x. Now, when you reach this time, which I will call t1, then you jump to some point y. And what is y? Well, I will follow my Markov chain. So psi 0, it's x. So this point will be psi 1. So I jump to psi 1. I just following this Markov chain. So in my example, psi 0, it's x. So I jump to psi 1. And now at psi 1, I will remain in psi 1 for an interval of time. So that will be t2. And this interval, it's of size t1 divided by lambda of psi 1, and so on. Okay? Now, at this time, tau 2, so I'm taking it left continuous, so I jump to a new point, which is psi 2, and there I remain for an interval of time, which is of size tau 2 divided by lambda of psi 2, and I call this time t3, and so on. Okay, so this is the way in which I will define. So if I want, now I have a time t here, so here is the value of xt. So that will be one trajectory I will follow. Okay, so my notations, so here x will, it's how I represented psi 0, so actually this is tau 0 divided by lambda of psi 0. So mine psi, it's an element of E, so lambda of psi, it's a positive number. And, okay, so my notation will be that this will be S1, sorry. So that's S2. And so now let's introduce my notations. So I'll introduce two sequences. A sequence SK, which I can start it from either 0 or 1. So let's say that we started from 1. And its definition, so xk is tau k minus 1 lambda psi k minus 1. Okay, so this is the definition of this sequence. So the intervals, the length of the intervals. And then the total length, so t 0 will be 0, and tk will be the sum for j from 1 up to k of sj. So these are the jump times. So at time t1 you have the first jump, time t2 you have the second, t3 you have the third, and so on. And now I will define xt. So if you want to know what's xt, you have to look at which interval it belongs. So I will look at k or n larger than 0 on the set at which t belongs to the interval tn plus 1. So this is 1 if t belongs to this interval, and it's 0 otherwise. So in this interval, so in the interval t2, t3, you are at psi. So this is psi n. Okay, so in the interval tn plus 1, the value of xt is equal to psi n. All right? So this is my definition. So you see that, well, I'm defining these variables, which now are indexed by r plus, with this chain and these times, but these times are functions only of these times tau. Right? And so what so two notation. The first one, so I have here, as I said, a probability. I'm assuming that all these variables, I didn't say it, but that all these variables are f measurable. So psi are f measurable and the tau are f measurable. P, it's a probability, so now px will represent the probability p condition that psi 0 is equal to x. So that I'm starting at x. Okay. So this is the process which starts at x. And ft will be the sigma algebra, so all the information available at time t, which means the sigma algebra generated by the random variable xs for s less than t. So it's clear that xt is ft measurable. And the main theorem I want to prove today is that if I take a function f at t plus s given ft, okay, so I'm computing the conditional expectation of a function computed at time t plus s given everything up to time t, so that this is equal to, it's like starting the process at time 0 at the position xt and computing fx, which is the Markov property. So we'll be proving that the process I just defined is Markov, if I define this property to be the Markov property. Okay? So is the definition clear?
What is f is variable function?
Sorry?
F is an variable function.
Yeah, f. So you see xt takes value in E. So f, it's a function from E to R. Okay, xt, in my definition, it's one of the psi n. And psi n, it's takes value in E. So xt takes value on E. Mind that Tn, it's converging to plus infinity almost surely. Okay, because Tn, it's equal to the sum sk, but sk, it's tau k minus 1 lambda psi k minus 1. Okay, and this is bounded. So these lambda, as I told you, takes strictly positive values. Okay. So this lambda, it's bounded below by the minimum. And so this is bounded by 1 over the minimum for x in E of lambda x times tau k minus 1. So actually, okay, so this is a constant times k from 0 to n minus 1 tau k. And I know that if I divide that by n, this is converging almost surely to 1. The expectation, these are IID random variables. So without the n, this is converging almost surely to plus infinity. Okay? And well, okay, I did it wrongly. I want the lower bound, sorry. So I want to show that it converges to plus infinity, so actually I need the lower bound. So this will be bounded by the max. And now I can argue. So this is converging to plus infinity, and therefore tau Tn, it's converging to plus infinity. And therefore, I mean, for any t, it belongs to one of these intervals. Okay. There would be a problem if Tn was converging to some fixed T0, how to define xt for t larger than this T0, but this is not the case because Tn is converging to plus infinity. Right? So the xt, it's well defined by this observation. This is the theorem I want to prove, and this is the definition of my process. It's clear? Fine. So the first result is that psi n Sn, it's, well, mind that x takes value in E times R plus. So we have seen Markov chains taking values in finite sets. This is clearly not a finite set, but I want to say that in some sense this is a discrete time Markov chain. So I want to compute the value of xi n plus 1, a function of xi n plus 1 Sn plus 1, given xi 0 S0, xi n Sn. Okay? So let's compute this conditional expectation. So as you see, S0, it's a function, so, and sorry, this is S1, Sn. So, yeah. So, okay, let me define S0 as 0 to include it here. So I know that the values of xi 0 up to xi n. And now S1, Sn are given by this formula. So S1, it's tau 0 lambda of xi 0, tau n minus 1 lambda xi n minus 1. So these are S1 up to Sn minus 1, Sn. Okay. So what I'm claiming is that this sigma algebra is the same thing as the one generated by xi 0 up to xi n and tau 0 up to tau n minus 1. So actually, what I'm computing is the conditional expectation of f xi n plus 1. Here, Sn plus 1 is tau n lambda xn, given xi 0 up to xi n, tau 0 up to tau n minus 1. Okay, since the sigma algebra generated by these variables are the same as these ones, so actually I'm conditioning over these variables. Now, how do I compute such conditional expectation? Well, I have to remember the definition of these variables. Xi, it's a Markov chain. Okay? And these variables, tau n, are IID exponentials, independent from the xi's. So maybe let me try. I would like to keep in one. Yeah. Just a second, let me finish to copy these. So, what's the question?
If we can work without discretizing the chain.
Okay. So what we are doing today is I'm constructing a Markov chain. I'm constructing a process, and I'll show that this process is a Markov chain. Okay. So we could, and why I'm doing that, so that you understand exactly what a Markov chain is. Continuous time Markov chain in a finite state space. Okay. Once you look at this, you understand what the process is doing. I could have started with another definition, saying that this is the definition. Okay. I have a process xt on the space which satisfies this condition. And then I will prove that actually I can construct these variables, tau and xi, and I can represent that chain in this way, with this formula. Okay, so I could have defined, well, what is a Markov chain? Markov chain is a process which satisfies this, and then prove that I can represent this Markov chain. So I can, in a space, construct these variables, construct this process, and that the distribution of this process coincides with the distribution of that process. Okay? But I prefer to do it in the other way around so that you see what is a continuous time Markov chain. Okay, so let's continue here. Now, I have to use the assumptions. So I know that tau n, it's independent from everything here. Okay, tau n, it's an exponential, which is independent from the Markov chain, so independent from all xi's, and independent from tau 0, tau n minus 1. So this conditional, I know that, well, the conditional expectation coincides with the expectation when I have independent variables. So I can, so this is equal to the expectation of f psi n plus 1. Here, S lambda psi n, an integral from 0 to infinity, exponential minus S ds. Okay. So tau n is distributed according to an exponential. The exponential has a density, so I'm just integrating this variable with respect to the density, and this is given by psi 0, psi n minus 1, psi n. And now, what remains, so I can move, if you wish, I can change the order of the integrations, and I have f of psi n plus 1. Now S divided by lambda psi n given psi 1, psi n, psi 0. But I don't need any more to, I could keep tau 0, tau n minus 1, but since psi, it's independent from this random variable, I can just forget. But if you are confused, you can keep tau 0, tau n minus 1 in this conditional expectation. But the fact that psi, here you have just psi, the fact that you have just psi, and you're taking the conditional expectation, and these xi's are independent from tau, you don't care. And now I can use, well, I'm conditioning in psi n, so lambda of psi n, it's known. And I know that psi n plus 1, it's a discrete time Markov chain. So this is equal So I know that at psi n, I'm at psi n. So this is the probability that I jump from psi n to a point y. And this is f of y s divided by lambda psi n. Okay? This is the conditional expectation. So it's a conditional expectation which depends only on psi n. Okay? So I prove that this whole conditional expectation is actually something which depends only on the value of psi n. It doesn't depend on the value of tau 0 up to tau n minus 1. And what I claim that this is exactly the expectation starting from psi n and 0 of f psi 1 s1. So here, I'm considering, so this process, so I'm saying, well, you're starting from psi n 0, or psi n, or, okay, you can put it here if you wish, Sn, because it doesn't depend on that value of this object. So let's compute this expectation to, so let me prove this identity. Okay, I claim that this is true, so let's prove it. So you have this Markov chain, you start from this point. So you start from a point x and r. So x is an element of E, r it's an element of 0 infinity. And you want to compute what is the expectation of this object. Okay? Well, by definition, this is psi 1, and S1, it's tau 0, or tau 0 divided by lambda of psi 0. Okay? So psi 0, it's x. And how do I compute this expectation? Well, first, tau 0, it's independent. It has an exponential, it's an exponential random variable, independent from psi. So this expectation, it's equal to the integral from 0 to infinity ds exponential minus s of f psi 1 s divided by lambda of x. And now, psi 1, psi, it's a Markov chain. It starts from x. So this expectation, it's equal to the sum over all y in E of the integral from 0 to infinity ds exponential minus s f y s lambda of x p xy. So it's the probability that the chain jump from x to y, which is pxy. In that case, I'm at y, and this is equal to that. Okay, so this is the computation here. And you see that this is exactly what's here. What is here, in which I have x here, it's psi n. So this is why I have psi n. And this value here doesn't appear in this formula. So the value r doesn't appear in this. So this, on the second coordinate, the probability that you jump from r to s does not depend on r, does not depend on the point at which you're starting. And so this proves that indeed the sequence psi n plus 1 or psi n s n, it's a Markov chain. And it tells you what is the jump probability of this Markov chain. So I insist that what we studied in the first 3 lectures were Markov chains taking value in finite space. Here the space is not finite anymore. The space is infinite. But what we are showing is that if you are at xr, you jump to ys with a probability which is pxy. You jump from x to y with this probability, and then you jump from r to s. Well, this probability does not depend on the starting point, and you jump to s with a probability which is exponential minus s. Okay. ds. So you go from x to r to ys with this probability. Now, I have here to, okay. So let me just, this is not really true. It's lambda x s lambda x. Okay, because here I have s over x. So let me change variables to write this. Sorry about that. So I will rewrite this sum as a sum over y. So I'm changing variables here. I'm calling this s prime. So I'm still integrating from 0 to infinity ds prime. But now s, it's lambda x s prime. So I have here minus lambda x s prime. And ds will be lambda x ds prime. And now I have f y s prime. Okay? So this tells me that I'm jumping from xr to ys with probability pxy, and then minus lambda x s lambda x ds. Okay, so you have a chain taking values now on E times R plus, and it jumps from XR to this pair with this rate. And mind that this measure does not depend on R. Okay, so it's a discrete time Markov chain with that transition. It's not a matrix anymore with that transition measure. So I define the measure in E times R plus, which tells me it's clear, or you're confused? Or you're confused by the fact that it's now continuous, because the way in which you may think is that Px, y, it's actually a measure on the second, it's a probability measure on the second coordinate, right? Which tells me what is the probability that I will jump from x to this point. So it's a measure which depends on the starting point. Now, if you have a process on E times R plus, what you'll have is that for each point in E R plus, you have a measure. But a measure on this space. So P XR has to be now a measure in this space. Okay? And which measure it is? Well, the first one, it's discrete. The second one, it's continuous. So this measure, if you, maybe I'll write it PXR. So it's a measure on Y ds. Okay? So it's a discrete in the first, continuous in the second. And this is exactly this measure here. So it tells me that if I'm at XR, then I will jump to YS with this measure. Mind that if I integrated that over S and over Y, I get 1. So it's a probability measure on this space, E times R plus. Okay, if I integrate it over R, I get 1. And if I sum over Y, I get 1. And this is, and it's a very simple measure, Markov chain, because the jump does not depend on the value of the second coordinate. Okay. Questions? Okay, so this is just a first result. Just that to get you familiarized with these notations, what's going on. Do you want me to compute other things, or can we go directly to the proof? So the notation, it's clear in your mind? Okay, so we can go to we could compute other expectations just to get you in the mood, but we can so turn to the proof of our theorem, which I remind you, it's to show that this process, it's Markov. So I want to compute xt plus s given ft. And I claim that this is the expectation of xt f xs. So in order to prove that, since this object is clearly ft measurable, I have to show that for all a in ft, the expectation of the indicator of a f x t plus s, that this is equal to the expectation of a xt f xs. Okay, this is what I want to prove. I'll fix a set A in ft, so which is measurable with respect to all xs, and I want to prove this identity. Fine? Okay. So let me draw a picture. So here's t, here's t plus s. And the first thing I will do is I will find an interval Tn, which is the one which contains t. So I will rewrite this expectation as a sum for n larger than 0 of the expectation of A, then the fact that Tn it's less or equal than t, less or equal than Tn plus 1, and then I have x t plus s. Okay. So in this case, I claim that since A belongs to ft, which means that I know A if I know xs from 0 up to t. But if I know, so here I have psi n, right? At this point, until this interval, the value of xt, remember, it's equal to psi n. Okay? So at this point, I jump to psi n, and I remain up to psi n. And Tn, it's the sum of sk and it's the sum of sk, it's tau k minus 1 up to lambda psi k minus 1. So what and well, Tn plus 1, and this interval here, it's just tau n divided by lambda psi n. So what I claim is that if I know psi 1 or psi 0, psi 1 up to psi n, and if I know tau 0 up to tau n. So I will know this interval. I'm assuming that t belongs to this interval. I claim that a, so if I know all these variables, and if I know that t belongs to the interval tn plus 1, then I can reconstruct my path up to time t. Because if I know all these variables, I can reconstruct my path exactly up to time t. And therefore, A belongs to the sigma algebra generated by these variables. So what I'm saying is that in this set, in which t belongs to the interval tn plus 1, if A belongs to ft, then A is measurable with respect to these variables, which means that if now here I take a conditional expectation with respect to psi 0, psi n, tau 0, tau n, this set it's measurable with respect to these variables, and A also. So this gets out from okay. And there is a sum. Fine. So now the second thing is to change the value of xt plus s. So I will introduce a second. So I have here tau n plus j, tau n plus j plus 1. So it will be somewhere. So this is equal to the sum for n larger than 0, and then now j larger than 0, because t plus s could be here. And well, if t plus s, it's the interval tn plus j plus 1, psi x t plus s, it's equal to x n plus j. Right? So I can replace right? And now I will compute this conditional expectation in a similar fashion that I computed the previous. So I'll stop this computation. I will concentrate on this conditional expectation. So I'm computing this conditional expectation. Right. Well, I will just write everything in terms of my variables tau or s. So Tn, it's a function it's Tn plus Sn plus 1, and Sn plus 1, it's tau n divided by lambda of psi n. So this is the first indicator, and then I have the second indicator, which is Tn plus Sn plus 1 Sn plus j. Then f of psi n, and this is condition on psi 0, psi n, tau 0, tau n. And I will proceed again by claiming that these variables in which I have tau n plus 1, tau n, sorry, and up to, so there's something which I don't like. in this computation is that I don't want tau n in my conditional expectations. Yeah, so I will not condition immediately on these variables. Let's go back here and let's condition only on ft. So let's go back to where we started. And instead of conditioning in psi 0 and so on, let's condition on, well, first, let's see at which interval t belongs. So this is OK. And now, well, it's ft measurable, so I can take it out from the conditional expectation. And tn less or equal than t is also ft measurable. So I can take out this first, but not the second. So this is exactly what I wrote here, but now instead of using this, I have here ft. Fine, and I want to compare So what was my argument? Okay, I missed an argument to claim that this corresponds to but in some sense I'm claiming that conditioning on ft, on this set in which tau n is less or equal than t, corresponds in conditioning on psi 0, psi n minus 1, tau 0, up to tau n minus 1. So what I will do, I will compute this conditional expectation and use this result in order to prove. So let me compute the conditional expectation of the indicator that t is less than tau n plus 1, that tau n plus j it's less or equal than t plus s less or equal than tau n plus j plus 1, given psi 0, psi n, tau 0, tau n minus 1. Okay, I will compute this conditional expectation. I'm stopping the proof here, and I will use this computation in order to get that result. But let's compute this. And maybe I'll try to prove this claim, but if I'm not able today, I'll bring that tomorrow, but at least let's compute this so that because that will be needed in the proof. So what I want to compute is this conditional expectation. So I'm assuming it's smaller than tn plus 1, and I'm computing this conditional expectation on the set in which tn is less or equal than t. So t it's exactly in this interval. Because tn, well, tn it's measurable with respect to these objects by its definition, right? Because it involves only up to tau n minus 1. And now we will, to compute this conditional expectation, we'll proceed just as we computed the previous conditional expectation. So we will just rewrite tn in terms of the variables tau. So this is equal to t less than tn plus, so I'm writing tn because tn it's measurable with respect to these variables, plus Sn plus 1, but Sn plus 1 it's tau n divided by lambda psi n. And then I have a second conditional expectation, of course, and here I forgot the fx plus t. Okay, so there is still fx plus t. So the second indicator, I will write it as Tn plus Sn plus 1, which is tau n lambda psi n, plus tau n plus j minus 1, lambda psi n plus j minus 1. This is less or equal than t plus s, and this is less than tau n plus tau n lambda psi n. And now I go up to tau n plus j, lambda psi n plus j. And then I have f of xt plus s, but I know that in this interval, xt plus s, it's equal to psi n plus j. And this is conditioned on psi 0 up to psi n, tau 0 up to tau n minus 1. Right? Now, these variables, they are all independent. So tau n, all these variables are independent, and this conditional expectation, it's just to integrate it with respect to these variables. So let me call t hat will be tau n minus t, because as you see, I have here tau n minus t on all sides. So let me just simplify notation by introducing tau hat as tau n minus t. And now I'm integrating over tau n up to tau n plus j, okay, which do not appear in this conditional expectation and which are independent from everything. So this is equal to the integral of tau hat, which is, so this expectation becomes this inequality, it's tau n minus t, but this is what I called tau hat plus tn lambda psi n. So this is the integral of d, let's say S0, the integral that tau hat plus S0 divided by lambda psi n, it's positive. Then tau n so let me subtract t on both sides. So I have tau hat plus, so tau n is what I'm calling as 0. So Sj minus 1 divided by lambda psi n plus j minus 1 less or equal than S, less than tau n minus hat, which is tau hat, plus S0 lambda psi n plus Sj lambda psi n plus j, f psi n, and then I'm integrating with respect to exponential minus S0, exponential minus S1, until exponential minus Sj, ds0 up to dsj. And then the conditional expectation, and now nothing depends anymore on these variables, so actually this is conditioned only on psi 0 up to psi n minus 1. but you can keep, if you wish, xi n. So tau 0 up to tau n minus 1. But they do not play any role anymore. It's okay to this step? So I'm just using the fact that these variables tau are IID. Now let's use the fact that these xi's form Markov chain. So by taking the conditional expectant with respect to xi 0 up to xi n, so xi n it's known, but all these variables are not known, so I will make a sum. On all possible values for, so what appears it's xi well, xi n plus 1 up to xi n plus j. So x1 up to xj. So these are the possible values of xi n plus 1 up to xi n plus j. And I'm starting, I know that this is a Markov chain, I'm conditioning from up to xi n. So it's like starting a new chain at time 0, starting from xi n. So what I get is that this is the probability to jump from xi n to x1, from x1 to x2, up to from xj minus 1 up to xj. So these are the possible values of the xi's. And now, well, I have all these integrals, xi n plus, I'm sorry, here is xi n plus j. Xi n plus j, it's x n plus j. Well, okay, I have to write everything now in my integral. So I have an integral in ds0 up to dsj, right? And exponential minus s0 plus sj, fxn plus j, and the indicators that, so the indicator is that so S0 divided by lambda of psi. So let's write this as x0, S0. It's larger divided by lambda x0. It's larger than minus t. So maybe I did the wrong choice. So maybe let's call this minus, I don't know, minus h, okay? So h will be, I should have defined t minus tn because t is larger than tn. So here I did the wrong choice. So let's call instead h t minus tn, which means that h it's minus t bar, okay? Just to have something positive. Otherwise, I'll mix everything up. So this is minus t, it's actually h. And h, at some point, it will be, so it's t minus tn. Okay, so this is the first indicator. And then I have, okay, here it's minus h. So I have all this sum minus h. So S0 lambda psi n, let me put it minus h plus S1 lambda. So I have here, the second term will be psi n plus 1, but psi n plus 1, it's x1. So this is lambda x1 plus, I guess, sj minus 1 lambda xj minus 1. This is, should be less or equal than s, which is less than S0 lambda psi n minus h plus S1 lambda x1 plus now Sj lambda xj. So this is the conditional expectation. Do you agree? I mean, the computation, it's awful, but it's not difficult. We have long expressions. Are you following, or you just gave up? Okay, well, it's awful, but it's simple. Okay, I just use the fact that it's a Markov chain, and I'm replacing the values of psi n plus 1 up to psi n plus j by all possible values, which are x1 up to xj. Now, okay, we are almost there. Let me change variables and call this R0. So R0 will be S0 divided by lambda xn. R1 will be S1 divided by lambda x1, and so on. So these are, okay, I have the sum over x1, xj. P psi n x1, xj. So instead of writing p xn x1, psi n x1, etc., let me simplify the notation in this way. And now I have these integrals, but I changed the variables. So all these integrations are in R+. So they are still in R+. So it's R+ to a power which is j plus 1. And now I have, when I change variables, I have lambda psi n lambda x1 up to lambda xj exponential minus lambda xn r 0 plus lambda xj r j. Is that correct? Yes. And this is dr1, dr0, drj. And now I have the indicator. okay, I have f, x, this is not xn plus j, but now it's xj. So you missed that. And here, with my new notation, this is just R0. It's larger than h. And R0 minus h plus R1 plus Rj minus 1. This is less than S, which is less than R0 minus h plus R1 plus Rj. So it's becoming simpler. Yeah.
You are integrating this character with respect to the R, or that should be an extra expectation?
No, I'm integrating now with respect to dr0, drj. So the r's are integrated, and the x are summed. So everything here depends only on psi n, and on this h, where h is t minus tn. So now the only random variables appearing are psi n and tn. Okay? Well, last change of variables, let me call here the variable R0, it's integrating starting from h, not starting from 0. So let me define R0 prime as R0 minus h. So now R0 prime, it's integrated from 0 to infinity. So that indicator will disappear. And here I will have R0 prime as well as here. And the only thing which will change is that here R0 will be R0 prime plus h, minus h, plus h. Okay? So h is fixed, so it will give me an exponential minus lambda xn h. So this is equal, so I get this minus lambda psi n h, if I didn't mix up signs, and then a sum x1 up to xj, same thing as before, p psi n x1 xj, integrated in r plus j plus 1, dr0, how do I call prime, dr1, drj, exponential minus lambda. Okay, I forgot the lambdas. That didn't change. Lambda psi n, lambda x1, lambda xj, exponential minus lambda psi n r0 prime plus lambda x1 r1 plus lambda xj rj. And the last indicator, so this one disappeared. It's just that R0 prime, it's positive, but it's included in the integral here, which I'm integrating R plus. And so I remain with this one, which is that R0 prime plus Rj minus 1 is less or equal than S, which is less than R0 prime plus Rj. Okay? Questions? So, what appeared here is just what I claim is that this is equal so this is what we are computing. And H it's T minus Tn. So what I claim is that this is equal to exponential minus lambda psi n T minus Tn, which is H, and then all these sums are nothing more than the probability that your chain is starting from psi n and that these, so here you're summing the first up to the first one, which is distributed according to an exponential of parameter lambda psi n, the second one lambda x1, but you jumped to x1. So this is what I claim is tau tj less than s less than tj plus 1. And sorry, I have f also, so this is an expectation of the indicator that tj it's less or equal than s, less or equal than tj plus 1, f of psi j, but psi j in this case it's fx. So what I'm claiming is that this long expression, which appeared here, it's exactly equal to this one. So this first expression is this one, and all the sum and the integrals are actually exactly like that. And here just the fact that what I have here it's psi j, but in the set in which s it's between tj and tj plus 1, xs and psi j are the same. So I can replace psi j by s, by psi s, xs. So do you agree with that or?
Yes, but I think maybe we should put an expectation there, because this character is a function that depends also on the abstract space. So I think you are going to copy the expectation from the
No, because you see all the variables R0 prime, R1, Rj are integrated.
But there is also the omitted, isn't there an omitted variable from the abstract space in the character?
It depends only on, so omega appears only in psi n and in h, which is t minus tn. Otherwise, everything else are integrated. Sorry?
Will it appear in the character?
In the characteristic?
Yes.
Well, in the characteristic, I have only r's. Because once I changed variables, the h disappeared. because I had here h, but when I changed variable, the h disappeared from this characteristic, this indicator function.
Can you discuss it, right?
Yeah, sure. Any other question? Okay, so what I'm claiming is that this long expression here, it's nothing more than this expression here. So maybe you agree or you don't agree, or you're not sure and you have to protest. Okay, if nobody complains, I will just assume that you all agree. Okay, so what I did, it's to show that this conditional expectation, it's equal to this expression. Okay? So okay. You don't look very much convinced, but you also don't complain. So what I suggest you to do is to try to compute it again. And if you have problems, we discuss it tomorrow. And then tomorrow, I will use this identity in order to conclude the proof that X is a Markov chain, continuous time Markov chain. Okay? So we stop here, and we continue tomorrow with the end of the proof. And we discuss now if you wish.